their coffee or tea or bagel or cookies. Okay, good morning everybody. We have dealt with reciprocal space in the last couple of lectures. Today we'll go a little bit further in that, and we'll be talking about structure factors. And you've seen that already on one of the handouts somewhere. I think I promised you that we will get back to them. So here we are. Structure factors are really the thing that allows you to get more than just a unit size, a unit cell size or shape from your diffraction data. So these are very important when it comes to actually getting a crystal structure. Once again, we need to expand some convenient concepts. But the good news is this is the last time that we have to do that. Okay? So we are almost there. Originally, we introduced the concept of reflection of X-rays from lattice planes, right? And that was a nice concept because it allowed us to come up with a very simple drawing and derive Bragg's law, which describes to us where we see diffraction, right? So we could derive Bragg's law and we could actually explain where we saw diffraction. The next thing that we introduced was we said, okay, it's not really a lattice plane, right? We get scattering from all of the atoms. And what we kind of then did was we made a simplified view of things by saying, okay, we can consider all of those atoms kind of accumulated in a lattice point, which is how we draw Bragg lattices, right? Where we have the dots at the corners, at the centers. That doesn't mean that the atom has to sit at 0, 0, 0. It's just much easier for us to see what the relationship between atoms is. Once again, that allowed us to figure out where the diffraction spots, where the spots in the diffraction pattern were. But who says that all the atoms have to sit on a certain lattice plane that I described? Who says that all the atoms have to sit where I draw reciprocal lattice, where I draw lattice points in a Bravais lattice? In most cases they won't, right? If you think about a real life material. In most cases there will be atoms throughout the unit cell. And if I draw any given plane, what are our chances of having all the atoms on there? 0, right? It's not going to happen. So, what we do know is any atom will scatter X-rays. Right? So we have to worry about those atoms that are not on one of those planes that we draw. And what we need to address is, what does that do to our scattering amplitude? Now, what we did derive in the last couple of lectures was a general scattering equation. That equation did not make any assumptions. In the end, we only dealt with a certain part of it, which was the summation part, which goes back to the unit cell repetition. However, there was a term in there that really applied to everything. And that's what we'll be looking at a little bit today. Now, to put it back into something that we can draw and that we can envision, let's just assume we are drawing our lattice planes, but there are some atoms that are not on a lattice plane, they are between lattice planes. Okay? It's simple enough drawing, isn't it? Here's one of your planes. Here's your next plane spaced dHkl apart. And there is this atom A that is sitting at a distance dA from the original plane. Now, as long as all the atoms scatter X-rays, if atoms on this plane and on that plane will scatter in phase, which means the path difference will be equal to a multiple of lambda, right? Then an atom sitting here in this plane A has to be partially out of phase with the other waves, right? Now, on this drawing, they actually say out of phase. What they mean is partially out of phase. It's not going to be exactly out of phase, in which case we would get extinction, okay? So, we have an atom that is sitting between the lattice planes that show constructive interference. So we get some kind of reduction in intensity. That's what we can already guess, right? Now, how can we describe this mathematically? Well, it all comes back to how do you describe a plane. I know not everybody here likes vectors, okay? But the easiest way to describe a plane is one vector, which is a normal to the plane that describes the entire plane. If you want to describe a plane by points, you need at least 3 points, right? So here's a little drawing. It shows you a plane with respect to an x, y, z axis system. Okay? And here's a vector p to a point P, which is in the plane. As you can see by this little symbol here, the vector P is perpendicular to this plane. We could, of course, describe this point with reference to the x, y, and z axes, right? We would basically say we take the projection along x, y, and z, and that gives us the coordinates of that point. That is probably what most of you are more familiar with, right? Because that is how we describe things all the way up through school. Now, there are several ways to describe a plane, okay? And one of them is the so-called intercept equation. And that may be one that you may not be that familiar with. Here's the intercept equation of a plane, okay? Now, we'll do a very simple derivation in 2 dimensions. So that would be intercept equation of a line. And that will hopefully make clear where these things come from, okay? If you work in 2 dimensions, x and y, we get what? We don't get a plane, right? We get a line. In 2 dimensions we can't have a plane. So let's draw a line that intersects both the x and the y axis. And let's call the x-intercept A, the y-intercept B, which is similar to what we would do in 3 dimensions in crystallography, right? A, B, and C. Now, how can I come up with an equation for that line? Well, first of all, how do I describe any line? There's that equation y equal to mx plus the intercept, right? And I already called that b, so that's certainly a good equation to use, right? A good variable to use there. So, if I know the 2 intercepts, I know 2 points of that line, right? Do 2 points perfectly define a line? Oh yeah. So one condition we have is when x is equal to 0, y is equal to b. Okay, that's kind of pretty logical, right? So we know that our intercept is b. My other equation is for what? For y equals 0, right? So when y is equal to 0, and we get the slope m times x, which is what? Right? So can we now determine what the slope of this line is? So our equation would be y is equal to minus b over a times x plus b, right? What we can now do is divide everything by b, okay? What we then get is y divided by b is equal to minus x divided by a plus 1. I just divided all 3 expressions by b. And if I then bring this x over a on the other side, then I get what is often called the intercept form of an equation. Okay? X over a plus y over b is equal to 1. Same thing will work in 3 dimensions. Okay, it's just not quite as easy to draw. So I figured I would show you how it is done in 2 dimensions. If you feel like it, you're welcome to try it in 3 dimensions. Okay. Alternatively, you know where it comes from, and you can just believe the equation that is given to you on that handout. Which, now no big surprise, reads x over a, and they call it AP, which is a projection of that point P onto the x-axis, plus y over BP plus z over CP is equal to 1. Makes sense, right? Intercept equation of a plane. Now alternatively, we can express these AP, BP and CP's as a function of the angles that the vector forms. Okay? This goes back to what we have used before. Right? Cosine of an angle is equal to one of the sides divided by the hypotenuse. Here's our 90-degree triangle. Here's the 90 degree. Here's our hypotenuse. Actually, here's the one for A, right? There's our distance P. So basically, the cosine of this angle would be equal to P divided by AP, right? So, if we multiply everything here by P, okay, then we would have P over this intercept times x plus P over this intercept times y plus P over this intercept times z is equal to P. Okay? We multiply an entire equation by a number. We are allowed to do that, right? And then we have these expressions here that say P over AP, P over BP, and P over CP. And that is simply the cosinus of each of these angles. Right? Because the cosine of this angle is equal to P over AP. So we can replace that P over AP by the cosine. And right now that might seem a little bit strange, and you might be wondering why we are doing that. It's one of those, if you know where you want to go, these things are useful. Okay? So you will see why we are going that way. So here's another form of the intercept equation. X times cosine of chi plus y times cosine of psi plus z times cosine of omega is equal to P. What does this describe? A series of planes that are located at a distance P from the origin. Okay. So what use is that? Well, now we have to go back to that atom between the planes, right? So, here's our first plane. Here's our general plane equation. And for that plane that is in phase, we know that this distance P has to be equal to what we call dHKL according to Bragg's law, right? We have derived that before. That is when we get fulfillment of the construct of interference. And the other thing that we know if we talk about dHKL is that we can use those Miller indices, right? Because where did the plane dHKL cut a unit cell? HK and L were the reciprocal of the intersections with the lattice constants, right? So, my intersection with A is equal to A divided by H. My projection on B is equal to B, the lattice constant B, divided by K, and the same for C. Okay? So these projections of that plane onto the x, y, and z axes can be described with respect to the length of the unit cell constants. That's how we defined the Miller indices to start with. So we can express things as a function of HKL and the unit cell constants A, B, C, which are not variables. They are fixed numbers for each crystal that we look at, right? That's a big difference. These A, P, B, P, C, P's will depend on what kind of plane you look at, where your atom is located, what the projection of that is onto the x, y, and z axes, okay? While A, B, C are not variables. They are fixed numbers. So, and we know that P is equal to dHKL. Now we did say before that the cosine of chi was equal to P, that distance, divided by AP, right? Oops. If you look at this drawing, cosine of this angle was equal to this distance divided by that distance. Now we just plug these things in. So instead of P we say dHKL. Instead of AP we say A over H. This looks complex, okay, but all we do is we substitute these things in here. So we can describe our three cosine functions with dHKL, ABC, and HKL. Okay? That kind of cuts down on the variables because who knew what those angles were? Isn't it much nicer to work with some straight numbers instead of cosine functions of angles that we don't know? So, that is basically what we can plug into this equation, okay? And that would hold for this plane at O prime. Now we did say we had an atom that wasn't sitting on that plane. It's sitting somewhere else in a plane A. This plane is not at a distance dHKL, is it? Otherwise it would be in the plane O prime. It's at a distance dA. And we could describe the coordinates of that atom with XA, YA, ZA, given that we just called it atom A. Okay, just to keep straight what we are talking about. Now, we can use this type of equation for that atom, right? Because we are drawing a plane parallel to the plane at which we were looking before that contains our atom A. So, we can still say that we have an equation like this. Now we just need to substitute the proper numbers in. Our atom is obviously at XA, YA, ZA, not at XYZ in the plane O prime. And our P here is no longer P, but is the PA or DA of that atom. Okay? So if we do that, the P becomes DA, the X becomes XA, and then for cosine of psi, I still use this expression, right? Because the angle won't change, never mind how far I go along that vector. Does everybody see that? So, I leave that expression in there. Let's do the same for Y and Z. It currently looks like a fairly ugly expression, but we can simplify this a lot, okay? One of them is, if I have an absolute value XA and I divide it by the unit cell constant A, what do I get? I get a fractional coordinate, right? Remember how we said heights are given in fractional coordinates? Same thing here. We can give atomic coordinates as fractional coordinates. So instead of saying my atom sits at 3 angstroms along the x-axis in a unit cell that is 6 angstroms long, I can just say my atom sits at x equal 1/2. Okay? And that is how crystallographers usually report their coordinates. So this is actually quite in line with what you will usually find Whenever you see small x, y, z, we are talking about fractional coordinates, okay, in crystallography. So that transforms these xa over a, ya over b, and za over c into small xa, small ya, small za. And of course, divided by means we multiply, right? So what we get is hxa plus kya plus lza times this common factor dhkl is equal to our dA. Does that look a lot simpler? Looks a heck of a lot better than where we started, doesn't it? No more cosines. Now, what we are really interested in though is the path difference, right? And what we know from Bragg's law is that the path difference is 2d sine theta, right? In this case, our distance happens to be dA, right? Now remember, we are still looking at the same diffraction direction, so it's still sine theta HKL. So our delta A, our path difference for that atom A, is equal to 2d sine theta HKL. And we can replace that dA by what we just derived, right? So we write 2d HKL sine theta HKL times this expression in parentheses. Now, this here should look familiar though. Doesn't it? What is that? According to Bragg's law, that's lambda. So we can replace this thing with lambda. So our phase difference, our path difference, is actually lambda times hxa plus kya plus lza. Who would have thought that it would become such a simple expression when we started a slide ago? As I said, sometimes knowing where you're going really helps, okay? So, that's our path difference. How does a path difference translate into a phase difference? Got to put that factor 2 pi over lambda in there, right? That is how we get the phase difference of the wave. And I guess we are not quite doing that yet. We will do it in a few slides. Now, alternatively, we could describe things using wave equations, right? Another thing that most people don't like, but we still do have to deal with them. Here's a generic wave. It has an amplitude WO, and it's described by some general amplitude. This is the maximum amplitude that that wave can have, and a cosine function of some argument. And I can choose several reference frames. I could use one where I go by 2 pi x over lambda, okay, where I look at the distance, or I could look at time, where I go with omega t. Either one is going to work, okay? It depends on your reference frame. This would be a wave that at time equals 0 or x equals 0 has the highest amplitude, right? That's how the cosine is defined. Cosine starts at 1. Now, if we have a second wave, they will have their maximum at another time or another x, right? That is what a phase difference means. And so we designate that wave with a different subscript, and it follows the same kind of frequency as the original wave, but there's a phase change in here. Okay? Now, if I have two waves, with an arbitrary frequency. So in this case they don't even have to be two waves of the same frequency, so they do have to have the same wavelength. Okay, that's the one condition, which usually holds pretty well because usually we work with one wavelength of X-rays. And I can write them like this. Both of them have some kind of a phase shift. I don't choose my frame of reference so that one of them happens to be maximal at 0. Then I can do some math here, okay, which makes it easier to sum them up. Now, this is another one of those rules that you might have seen at some point in time but may not remember. Here's a nice rule for cosine of A plus or minus B. And this rule actually says is the cosine A times the cosine B minus or plus, so the sign changes, the sine of A times the sine of B. Okay? And that is the rule that was used down here. You have the cosine of omega t minus a phi, which is equal to the cosine of omega t times the cosine of phi, plus the sine of omega t times the sine of phi. Okay, that's the rule that was applied there. Can you do the same for the second wave? Sure. Could you do the same for 10 waves, 20 waves, 100 waves? Yeah. What you will see is that all of them have some common factors. All of them have this cosine omega t and the sine omega t, right? And so when you sum these waves, you can actually get an expression where you say cosine of omega t times the sum of all these f's, of all the amplitudes, times the cosine of that phase, plus the same thing for the sine term. Okay? Now this is really what described the frequency of the wave, right? So as you can see, that is a term that we can draw out of that sum. It applies to all of the waves. And so if we had a whole bunch of waves, we could write this as the cosine of omega t times the sum of all fn times cosine phi n, plus the sine of omega t times the sum of all fn sine phi n. Okay? And knowing that we can write any wave like this, okay, we can also start to calculate the amplitude of a wave. What we will see here is that we can draw things apart, right? We have two parts to each wave equation. We have a cosine part and a sine part. As I just said, each of them has that sum of all the f's times all the phases, okay, which have to give the resulting amplitude and phase for the resulting wave. That sum of all of them. But I should be able to express that as one amplitude and one phase once I'm done with my math, right? I can always sum up the numbers. So I get two parts. And this f is the amplitude of the resulting wave. Now if I want to calculate what f is, I actually now have a way to do so. Okay? What I can do is I can square each of these expressions. I square the left hand side, I square the right hand side. Mathematically, that's a legitimate thing to do. So what do I get here? Well, f squared times cosine squared of phi, right? It's equal to this whole sum squared. Same for this expression down here. Now, if I sum the two of them up, I get f squared times cosine phi squared plus f squared times sine phi squared equal to this sum squared plus that sum squared. Does anybody know what cosine squared plus sine squared is? 1. Now that's convenient, because that means if I sum these two equations squared, then I get f squared times 1. Okay? Because it's the cosine squared and the sine squared of the same argument. That means that f is equal to this sum squared plus that sum squared and the square root out of it. Okay? And that is the equation that is given down here. So, if we know all of these phases of all the waves and all of the amplitudes of the individual waves, we can calculate the amplitude of the resulting wave. That's what that equation says. Aren't you glad we have computers already? Now, most people don't like to do math with sine and cosine functions. There's another way of representing these waves that are sine and cosine functions, and that is Argand diagrams. We talked about those already a little bit in handout 6, and I promise you would revisit them, okay? Here it is again. This is an imaginary plane, a complex plane, okay? You have the real axis and the imaginary axis. If you ever draw them, label them with an R and with an I, okay? The cosine is the projection on the real axis, the sine is the projection on the imaginary axis, okay? That means any wave that is composed of cosine and sine functions we can describe by a vector that is traveling on a circle. So our f, which is now a vector, is equal to the length of that vector times the cosine plus I times the sine, which we can conveniently write as e to the I alpha t. Because sometimes doing math with e functions is actually easier than doing math with sine and cosine functions. And it's this kind of expression that we will be using from now on, okay? Why are these vector representations so useful? Well, it's pretty easy to add vectors, isn't it? All you do is you draw tail to tip and you just keep drawing. And if I told you to sum 10 vectors, it would probably not take you very long to do so, would it? Take a piece of paper, draw it, okay, you've summed your vectors. How long would it take you to sum 10 waves that are described by sine and cosine functions? A lot longer, right? So this is much easier, okay? What you can also nicely see out of this is what we just went through on some of the previous slides, and that is, once you've summed up all of these waves, okay, look what the projection of the resulting wave on the real axis is. Oh yeah, it's the projection of the first wave plus the projection of the second wave. So what we were saying about the sum of all fn cosine of phi n, here we go, okay, still holds. So, for any number of waves, we can write that the f times the cosine phi of the resulting wave is equal to the sum over all atoms from 1 to n of fj times cosine phi j, and we can put up a similar expression for the sine part, because once again, all of the projections here would sum. And we can write the full wave as a vector f that is equal to the sum of all fj times e to the I phi j. Okay? So, now let's get back to making a phase difference out of our path difference. Remember that we obtained that equation. delta A is equal to lambda times hxa plus kya plus lza. Phase difference is simply 2 pi over lambda times this path difference. The lambda cancels out. So our phase difference phi j is equal to 2 pi hxj plus kyj plus lzj. This applies to those phi j's on the last slide for every single atom. Remember, we said we sum over all the atoms. So that means that our vector f, our amplitude of a wave, depends on the diffraction direction as described by HKL, which also would be the diffraction angle if you choose a more common frame of reference for ourselves. Okay? This is what describes the amplitude of your wave. And we call it a structure factor. You saw that word somewhere before on one of the handouts where there were Fourier transforms between real and reciprocal space. There was that word structure factor on there. And at that point in time it didn't mean anything to you. This is that structure factor that was on that slide. Okay? You should usually write it as an FHKL, whether you put it in parentheses or as a little subscript, because it does depend on the diffraction angle. Okay? Every single reflection in your pattern will have a unique FHKL. And the one thing to keep in mind is this F has a sum of all atoms in there, right? That means you change one atom in your crystal, you change its identity, you change its position, every single reflection in your diffraction pattern will change. Okay? This is very different from NMR. We're changing one atom, changes the peak for that atom and maybe the next neighbors. Okay? This one atom will affect every single reflection in your diffraction pattern. All of them. Because of that summation. We can actually break down FHKL, okay? We could write it as having a real and an imaginary component, because we just went through the fact that we represent these waves as the sum of cosine and sine functions in the complex plane. And they are sometimes called A and B. Okay, so you might see these expressions that FHKL is equal to AHKL plus IBHKL, where A would be the sum of all the cosine parts and B would be the sum of all the sine parts. And as you can see, we have now put our expression for phi in here, for the phase difference. These are equations that you do want to remember. They are very useful. You will need them. So, one of the things you might be wondering about is, what are all of these FJs, right? Where do we get them from? Are they just arbitrary numbers? Do we guess them? What's the deal with them? They're actually called atomic scattering factors, okay? They depend on quite a few factors. They depend on the wavelength that you use for your experiment. They depend on what your atom is, the scattering angle, okay? What they really are in real life is they describe how efficiently an atom scatters X-rays as compared to an electron. So one single electron would have a scattering factor of 1. An atom that has more than one electron can have a scattering factor that is higher than 1. The maximum value that Fj can ever take is the atomic number of the atom. Okay? However, in many cases it will be a little bit smaller. And the reason for that is that most atoms don't scatter X-rays as efficiently as a localized electron, and part of that is an atom has size, right? So we may not encounter all of those electrons. Most of the time you'll find FJs, okay? If you were really precise, you should probably write it as Fj theta lambda, because it does depend on scattering angle and wavelength. What you usually get is there's actually a table that lists F values for all atoms as a function of sine theta over lambda, which absorbs both the wavelength and the diffraction angle in the international tables. Okay, so if you needed to do math, you would be using these values. All computers that do structural analysis based on crystallography will have these kinds of numbers somewhere in their programs. Okay, they use these actively. Now, back to our experiment. So what we really need are those F's, right? Because they contain a function that tells us where the atoms are. However, we don't measure F. Who has ever managed to measure a wave? Not really, right? So, what we usually measure is an intensity. How do we get an intensity? Well, the intensity is proportional to F times the complex conjugate of F. That's how you get an intensity. What's the complex conjugate of F? The only thing you do is you switch the sign in front of the I. That means you have the magnitude of F times e to the I phi, and you have the magnitude of F times e to the minus I phi. Right? So that means that we have an F squared that is equal to A squared plus AB times I minus AB times I minus I squared B squared, if you multiply this out. Okay? What's minus I squared? I squared is minus 1, so it's plus 1, right? Minus I squared. So overall you get that F squared is equal to A squared plus B squared. And this is actually the intensity that we measure. Okay? Now, there's nothing complex left, is there? Has certain advantages, right? That means we can actually do math with it. No eyes. So we like that. It also means that we lose the phase information. Okay? We get this. We get the magnitude. We don't really have that anymore. Okay? So we lose the phase information. And once we go back to how we actually collect data and how we deal with our data, you will see that that is often referred to as the problem in crystallography. The phase would really be given by the tangents of phi being equal to b over a, but usually we don't measure these parts separately. All we get is this. Okay? Now, why did I not say equal here? Well, there are a few factors that stand between I and F times F star. Okay? All of them change what we measure. One of them is thermal vibration of our atoms. They don't sit still in one spot, and they aren't point atoms. Okay? We'll have another slide that explains that in more detail. We have some basically geometrical factors. Okay? Lorentz factor. They depend on your diffraction geometry. They are usually very simple for most single crystal diffractometers. It's a simple 1 over sine 2 theta function. This correction can be applied directly by the computer. You never see it. Okay? You will have absorption. Samples don't just scatter X-rays, they also absorb them. So that reduces the intensity. Function is e to the minus mu t. Mu is the absorption coefficient, t is the thickness. You have a polarization factor of the X-rays. Once again, it's a fairly simple geometrical function. Then you simply have a scale factor, because simply lose some intensity. Some of it is scattered by air, some of it is just not detected. Okay? So you have a constant with which you have to multiply your data. So, what about that thermal vibration? That seems to be only more complicated factor in there, right? What thermal vibration does is, it makes an atom kind of more diffuse, okay? It smears out the electron cloud. The atom isn't just sitting here, it's wiggling around that position. Now, what does that mean? First of all of those atoms still scatter X-rays, right? But as we look at all the X-rays scattered at the same time, what it also means is we don't have an exact unit cell repetition, do we? Because who says that if my atom in this unit cell happens to be moving that way at a certain point in time, that this atom is going to be doing the same? Chances are they won't, right? Thermal motion is random. So that leads to a very, very slight phase difference. Okay? It's not a lot, but it will reduce your scattering intensity. This graph actually shows you what this does to the scattering intensity, okay? Here is a point atom with a certain number of electrons, Z. It would scatter like this as a function of angle. A real atom will show a drop-off in scattering magnitude with angle. Now, why is that? Well, if we go right centrally through an atom, so this would be a scattering angle of 0, right? Tiny little bit of movement won't make much of a difference. Okay? If we scatter at a higher angle, and all of a sudden it does make a difference for the phase difference. Okay? And that is what it all depends on. Do we get a phase difference from two atoms that are slightly displaced? So, the higher your angle, the more thermal vibration will actually affect your scattering amplitude. There's an equation that describes it. So your F for your atom should really be an F0 times this factor, which describes the thermal vibration. E to the minus bj sine squared theta over lambda squared. So there's your dependence on angle, okay? And this B is actually 8 pi squared times u squared, where u squared is the mean square amplitude of displacement. So this is a direct measure of how much those atoms move. Once you get into crystal structure analyses, some programs use this u, some programs use the B, okay? There will be a big difference in numbers. As a matter of fact, a difference of 8 pi squared. Okay? That's about a factor of 70 or 80. So, somebody reports thermal parameters to you. You need to make sure that you know whether these are U or B values, because otherwise you cannot judge whether those are reasonable numbers. Okay? Somebody reports a B to you that is 2, 5, maybe 10, something like that. Those are not unreasonable values. If somebody reports a U to you that is 5, it's worth nothing. Okay? So it's important to know what people are talking about, what their reference frame is. Important thing to remember is thermal vibration leads to a fall off in atomic scattering with angle. Now, what else are structure factors useful for? This one only has a couple of slides here, but this is quite an important topic. Systematic absences are something that crystallographers use a lot. What they are the fact that certain reflections will be systematically absent, as the name says, from your diffraction pattern. Now, the reason for that is that you have translational symmetry that is not a unit cell translation. Okay? Lattice centering. It's not the unit cell, right? That's somewhere within the same unit cell. Glide planes. Translation of 1/2, or in some cases 1/4 of the unit cell. Screw axes. All of them have a translational component. Okay? Simple rotations and mirror planes don't have translational components, they don't give systematic absences. Now, based on what reflections you do or don't see, you can actually assign space groups. So as you can imagine, that is a very important thing to understand. Now, how does this work, right? Okay, I'm telling you there are systematic absences. But how do they come about? So let's do a derivation for one example. Let's just, for the fun of it, take a body-centered system. Okay? So let's first of all draw the brevet. Where do I put spots in a body-centered system? In the center and on all the corners, right? Now this goes back to those lattice points that are so convenient, that we like to use, right? What does this really mean? If I have an atom at X, Y, and Z, what does body centering mean? What does body centering mean? If I had an atom at 0, 0, 0, what would body centering mean? Should I get an equivalent atom somewhere? Where? If I have an atom here at the corner, where's the equivalent atom? At 1/2, 1/2, 1/2, right? Absolutely. Now, as I said, these lattice points are a convenient thing for us because they make it easy to visualize. I can see a 1/2 translation, right? Not quite so good at picking up a 0.11 or something like that. But the same rules apply to your atom at X, Y, Z, okay? Doesn't matter whether X, Y, and Z is 0. So this is what body centering means. Any atom at XYZ has an equivalent atom that is related to it by the body centering translation. So that's X plus 1/2, Y plus 1/2, Z plus 1/2. Right? Now, in order to look at whether or not we see intensity somewhere, we need to look at those structure factors that we introduced today, right? So, what was our expression for FHKL? Was the sum over all atoms, right, of the atomic scattering factors times e to the I phi j. And phi j was 2 pi hxj plus kyj plus lzj. Right? So, if we had no translational symmetry within the unit cell, we would have to work with that expression for all atoms within that unit cell. But we have eye-centering. So we only need to describe 1/2 of the atoms, because we can express the other half, right? So all I did was I made use of the fact that I know that for any atom at xyz, I have an equivalent atom at x plus 1/2, y plus 1/2, z plus 1/2. So I write the two equivalent atoms, which means I only have to sum over half of the atoms, because I still have 2 times n over 2 atoms in this sum. And of course, if we look for systematic absences, we want f equals 0, right? If f is equal to 0, regardless of xyz, that's what we would call a systematic absence. So we need to do some math with this. Okay? And I'll just use phi j here for a moment, okay? We did define what phi j is. Just makes it easier to write. So all I did right here was I multiplied out that stuff, okay? This is where some knowledge of E functions comes in handy. Does anybody know what we can write instead of e to the power of a plus b? E to the power of a times e to the power of b. That's what we can do with the second expression here, right? That's applying that rule, isn't it? So that means that we have a lot of things that are equal in this sum. Which means we can draw all of these out and multiply this simpler sum with that, right? So all I did was I drew this one out of this multiplication. So our f is now the sum over all fj times e to the I2 pi phi j times 1 plus e to the I pi h plus k plus l. So now we have to ask ourselves, what do we make out of that, right? So we've done some math, and the expression has gotten a little bit shorter. That's usually a good sign. But how can we make it useful? Well, we are looking for systematic absences, right? So we are looking for how can this become 0 regardless of x, y, and z. That's our goal, right? That's what systematic means. Not dependent on atom positions. Systematic. Does this contain x, y, and z? Sure does, right? So this term will always depend on x, y, and z. How about this term? So what we are looking for, okay, is, and I assume everybody has copied this part. And the reason for that is if I have a multiplication and one of the factors is 0, everything gets 0, right? So if I multiply a sum that depends on x, y, and z with 0, my whole f becomes 0. That starts to look a lot easier, doesn't it? Now, who can predict E functions? Not that easy, right? But can we convert an E function into something more useful? E to the I alpha is equal to cosine alpha plus I sine alpha, right? That's our rule. If we apply that to that one, we get 1 plus the cosine of pi h plus k plus l plus I times the sine of pi h plus k plus l is equal to 0. What do we know about h, k, and l? What are they? They're integers, right? Now, what's the sign of pi? 0. What's the sign of 2 pi? What's the sign of 3 pi? What's the sign of any whole number times pi? Still 0, right? So the sine term goes to 0. Now isn't that convenient? Because that means we just lost the whole complex part. That is left. 1 plus cosine pi of h plus k plus l is equal to 0. Now, that means that cosine of pi h plus k plus l has to be minus 1, right? Where is the cosine? Minus 1. That would be true for pi. Where's it minus 1 again? Cosine of 0 is what? 1. Cosine of pi is minus 1. Cosine of 2 pi? Plus 1. Cosine of 3 pi? So if h plus k plus l give us an odd number, then this equation is true. Because then we have cosine of pi, of 3 pi, of 5 pi, of minus 7 pi. Doesn't matter. Cosine of an odd number times pi is minus 1. In which case this holds true. So f will be 0. And we have a systematic absence. So, any reflections where the sum of h plus k plus l is odd in an eye-centered system will be systematically absent. You will not observe them. Okay? That's a lot of reflections if you think about it. Now, sometimes you deal with absences. What you may recall from handout 5, okay? Let me see whether I can actually find that one. Actually, maybe I don't need it. Yeah, I actually don't need it. Good. All we have to do is go back to our handout. Has everybody copied this? So, now you have some idea of what these systematic absences are, okay? And how you get to them. Here's a slide that shows you a little bit from the international tables. What they give you is not something called a systematic absence, okay? They actually give you the opposite. And in handout 5 there was this part of the table that was called reflection conditions. And I told you that time, don't worry about it yet. That is what this is, limiting conditions, okay? Let's check our eye-centered. Here's our eye-centering, okay? And what it tells us as a limiting condition is h plus k plus l equal to 2n. Okay? Which means only reflections where h plus k plus l is equal to 2n are present. Because what they care about is what do you see. Now for the math part of it, you can deal with what am I going to see. All that you can derive mathematically is what do you not see. Okay? So that is why you have limiting conditions in some tables, but you talk about systematic absences in many cases. Because let's face it, the program is not going to look at things and say, oh, I see a reflection. The program is going to say, this is my unit cell. What are the reflections I don't see that should be there according to this unit cell? Okay? So, systematic absences, limiting conditions, really just two ways of looking at the same beast. This is a list of what all of these different translational components do, okay? centering. All of them do create some kind of abscences. Screw axes. As you can see, not all of them work on all reflections. Screw axes may only work on certain reflections. Screw axes along the A-axis will only affect the HO reflections. That comes from what kind of equivalent atoms are generated. Okay? Some of that stuff may just drop out. There may only be a condition on H left. You can go on and do this for any symmetry element that contains a translational component. Anything that has translation will generate systematic abscences. Okay? Don't memorize that table. It'll do you no good. Okay? Because if I ask you to derive some systematic abscences, I want to see that math and I want to see the rules spelled out. Just knowing the result is not going to help you if you don't know the rules, okay? If I just want you to use systematic abscences, you will actually be given a handout in the future that is a table of systematic absences, okay, that helps you assign space groups. And we'll be using that one. And there will be exams where you're told that you can bring it, okay? So in that case, you can look them up anyway. So there's no point in trying to memorize this table. Now, this is the end of the structure factor handout. And this is the end of the material that is fair game for exam 1. Okay? We will be covering another handout after this, but it will not be on exam 1. Anything up through this point and anything up through the third homework is material for exam 1. At this point in time, are there any questions? Because if there are not, then we'll be doing some practicing here and some actually seeing how this works. Okay? You always start, good question. The thing that you always start with, okay? Oh, come on. Is this. This is the general structure factor equation. This holds true for anything. Okay? What will change in each case is what I erased. What are your translation conditions? Okay? For body centering, your translation condition is x plus 1/2, y plus 1/2, z plus 1/2. And those are the ones that I do expect you to know, okay? We've looked at the Bravais lattices. You should be able to draw the little Bravais things, okay? And you should be able to figure out what the translations are. Because they make it very clear if you assume there was an atom at 0, 0, 0, where would another one show up? Same holds true for an atom at x, y, z. If I tell you that there is any kind of centering, I would expect you to be able to figure out what the translational components are. Okay? When it comes to other translational symmetry elements, glides, things like that, chances are I would tell you there is a unit cell that has the following symmetry operation that creates equivalent atoms at x, y, z and derive the systematic absences. So I would probably give you the translational component. Okay? The different types of centering, A, B, C, I, F, I expect you to figure out. Because they are pretty easy, right? The other ones, given that we really haven't talked about, matrix representations and how things correlate, I would give you what the translation is. But if I give you what the translation is, I would expect you to be able to do the equivalent math. Okay? So, other questions? If not, let's actually have a look at something that has some of these symmetry elements. some plane groups. Okay. Now, isn't that a neat exercise? Let's see whether we can find some symmetry elements in some of these. Review coupled with actually looking at our absences. Let's take the top one, A. Or actually let's start with something that has a little less stuff on it. Start with C. Who sees any symmetry in C? Mirrors? Which way? Both ways. So there's mirrors here, of course in the center. Mirrors there. Mirrors in the other direction. Like that. Anything else on that one? I heard a twofold here. Who sees the twofold? Several people. Where do we draw the twofold? Intersection of the mirror planes. Exactly. So it would be a twofold there. I will not draw it on top because my pen is just too wide for this size drawing, okay? There would be twofolds here. There would be twofolds here, all over the place, right? So, we have twofolds, we have mirrors in two directions. Do we have anything else?
Do we have a glide?
Do we have a glide?
Yeah.
Question for that is, what's your unit cell, right? Without a unit cell, you can't tell me whether there's a glide.
Well, forget it.
So let's first figure out a unit cell. I shall just, for the fun of it, choose my origin of my unit cell here. How far do I go for my unit cell? There, and there, and there, and there, right? I need the same thing at each corner of the unit cell, and that's indeed given. So now that we have our unit cell, Nicholas, do we have glides? No, right? So we have two folds and two perpendicular mirrors. Anybody want to assign a plane group here? P2MM. All right. How about we look at E? Mirrors. What direction? Up and down, yeah. Like that. What else? Two folds. Where are the two folds? The twofold right here between, right? In those locations. Right in these spots between each of those. There will be twofolds here. There won't be any twofolds though. Right in the middle here, okay? Don't draw those. What else do we have? Do we have any symmetry in this direction? Once again, we may have to assign a unit cell first. So let's pick a unit cell. We'll go from there. Now I can't go here, okay? Because that would not be the same thing. So I have to go over here. So unit cell seems to be the same size as the drawing above. Now, any symmetry in this direction? I hear glide. And indeed, if we drew a glide here, right, we would take this object, we would translate it by 1/2 unit cell, we would reflect it. Does that work? So there's a glide here, and if you do the same checking, there's a glide down here and up here at the edges of the unit cell. Anybody want to assign a plane group? P2MG. Alright, now let's see. Should any of these have systematic absences? Should that one have systematic absences? No. No translation, right? But about that one? How about that one? That one probably should have some systematic absences. Let's see whether it does. Ooh, that's of course way too weak here. Oh, we may have to turn off the light to really see this. There's one of them, P2MM. That is your P2MG. Do you see the difference? Watch the center line that is horizontal. Do you see how every other spot disappears when I go there? Okay. That's from the glide plane. The glide plane is the translation that makes every other spot disappear. Now, before we turn the light back on, there's your P2MM. This is the one above it. Did some spots disappear? So let's see whether we can figure out what that one is. Okay. This slide has exactly this stuff on it. Okay. It's just that at least this way we can do some kind of assigning of symmetry elements with it. So let's look at that top one, that A part. What are we going to do with it? Mirrors. Where? There are mirrors running down here, right? Running down there. And I'm just not going to draw them on there. I'm just going to leave them out here. Because if I start drawing on that one, we can't see a thing. There's glides. Where? In the other direction. Where would you like them drawn? Right here? Oh yeah, I can draw them. What else? Some more mirrors. Where? Right between the two glides? Now you really start seeing why I only indicated it on the edge, right? How about the other direction? There should be a glide horizontal between the two mirrors, right? Now we need to look for rotations, because we need to know what the highest rotation is before we can decide whether we can have diagonal elements, okay? If I have 4-fold, 3-fold, 6-fold, I can have stuff that is not horizontal or vertical. But if I only have 2 folds, then I can't. So, it's important to figure out, right? 2-fold. Somebody said 2-fold. Where? Everywhere, right? Like there, like there, like there, all over the place. So, does anybody see higher rotation symmetry? If you're staring at it confused, that's fine, okay? There actually is no higher rotation. Because if you look at, for example, this point right there in the center, there are 4 objects around it, but they are not going in the 4 corners. So it's not 4-fold rotation, okay? Like if you take that point here, this is not 4-fold rotation, although there are 4 objects around it. So, let's see whether we can figure out a unit cell on this thing. And let's just take something that we can recognize, which is that point between those 4. We look for the next one to find the next unit cell corner. We look for the next one, which would be over there. So there's our unit cell. Still the same size, right? You can already see that they did that on purpose on that side. Question we now have to answer is, what do we call this plane group, right? C2MM. Because the C absorbs the G, right? This actually gives you a nice example of what we just talked about, okay? This little thing is not sitting in the corner. It's not sitting at 0, 0. It's sitting at some kind of x plus y, okay? But if you do 1/2 translation through the unit cell, you meet the same object again, okay? So an object at xy also appears at x plus 1/2, y plus 1/2. If it was sitting right on the corner, that 2-fold also appears in the center, sure. But it works for anything. It doesn't have to sit at 0, 0. So that's C2MM, glides in 2 directions, and therefore systematic absences, as you saw on the little thing, in both directions. Okay. Systematic absences are a very useful beast for the crystallographer, because we have what? 230 space groups, right? In 7 crystal systems. If we didn't have systematic absences, we would have a heck of a hard time figuring out what space group our crystal adopts, okay? This is the bread and butter of figuring out what the structure, what the space group of your material is. Did that help a little bit to actually see how these things work? It's always nice to see an application of some strange math that we derived, right? So, that's the material that is fair game for your exam. One more lecture, then we'll play Jeopardy to review. Then we'll have the exam. Okay, you do have a homework. Do work on it. Don't leave it until Sunday. This one is work. Other than that, if there are no more questions, that would be it for today.